The gas laws. Let us discuss ye olde gas laws. So, 18th and 19th century, they decided that they were going to try and understand gas by looking at it real hard with numbers. So, what happens if I do this over and over and over again? They just did stuff to see what happened. So eventually they discovered 4 variables and 3 laws. The variables are pressure, which we talked about earlier, the volume of the container, the number of moles of gas. In fact, this is how they discovered the concept of the mole. And finally, the temperature of the gas. Absolute. This is always going to be in Kelvin. The 3 laws they discovered were Boyle's law, pressure and volume, Charles's law, also known as Gay-Lussac's law, volume and temperature, and Avogadro's law, volume and moles. So, what we're going to do is we're going to look at the law, we're going to do a little practice math problems with the law, and then we're going to use kinetic molecular theory to explain the law. So Boyle's law is the relationship between volume and pressure. So for any one of these laws, you're holding 2 variables constant, and you're looking at the other 2. So for pressure and volume, that means we need to hold the moles of gas constant, and we need to keep the temperature constant. So it's just a sealed container with, you keep it in an ice bath, basically, a temperature bath. You insulate it, okay, keep it at constant temperature. And then you can just change the pressure on the thing. Here they're using weights on top of a piston. That works just fine. And watch what happens to the volume. And as you might guess, if you squeeze the gas, the volume's going to go down. If you decrease the pressure, the volume's going to go up. Okay? More pressure, lower volume. Less pressure, higher volume. So, what Boyle found in particular was that the product of pressure and volume is constant. P times V is equal to a constant, K. Or P1V1 equals P2V2. Okay. So the initial pressure times the initial volume is equal to the final pressure times the final volume. So what happens to volume if you double pressure? So, boop. All right, so if you double the pressure, that means that the final pressure is equal to twice the initial pressure. Okay. So P1V1 equals P2V2, but P2 is equal to 2P1. Okay. So we're looking at 2P1 V2, so P1V1 equals 2P1 times V2. So divide both sides by P1, and V1 is equal to 2V2. Or, to put it another way, V2 is equal to V1 over 2. If you double the pressure, you're going to cut the volume in half. If you triple the pressure, you're going to cut the volume down to 1/3. And if you cut the pressure in half, the volume would double. Now, what if you have a system that starts at 150 milliliters at 1 atmosphere, and you increase the pressure to 1.250 atmospheres? Well, that's a little bit less obvious, but once again, we just plug the numbers in. So P1 was 1 atmosphere. V1 was 150 milliliters. P2 is 1.250 atmospheres. And then we're looking for volume 2. Okay. So basically it's 150 times 1 divided by 1 1/4. So we're dividing by 5/4, so it's going to be, let's see, multiplied by 0.8, so 125 mils. Let's double check that. So 150 divided by 1.25, that's 120. 120 mils. All right, so you increase the pressure a little bit, the volume's going to go down a little bit. Okay. So a Boyle's law problem is relatively straightforward. You identify your initial volume, your final volume, or your initial and your final conditions, and you look for the one that's missing. Okay, so in this case, we were looking for the final volume. All right, so let's continue. Kinetic molecular theory, explaining Boyle's law. So Remember, pressure is force divided by area. Okay, so in all of these situations, when we change one of these things, we'll be changing either force or area, or possibly both. So the moles are constant. Okay, so the number of particles are constant, so the number of collisions is constant. Temperature is also constant, meaning the speed of the particles is constant, so the force of each collision is constant. So the force the force aspect of pressure is being held constant here, but volume can change. So the total area inside the container can change. So that is how pressure inside the system can change. So when we increase pressure from the outside, what's happening is we're creating an imbalance. The pressure outside is greater than the pressure inside. So the piston starts to slide downward. Okay, meaning that our volume is decreasing. And as walls disappear behind the piston, that means the area inside the container is decreasing. So as area decreases, the pressure inside the cylinder is increasing because you're dividing by a smaller number. Eventually, the pressure inside once again equals the pressure outside, and the piston stops moving. So that is just a very direct physical explanation for Boyle's law. As you change the thing, you get an imbalance, and then the system shifts until balance is restored. All right, so now for Charles's law. With the relationship between volume and temperature. Now we're holding pressure and moles constant. Okay, so it's still a sealed container with a certain amount of gas inside, and then we have a certain external pressure, and that external pressure isn't changing. But volume can still change. This piston is still free to move up and down. So what happens if you change the temperature of the gas? Well, if you heat the gas up, the system is going to expand. If you cool the gas down, the system is going to contract. So what Charles found is that the ratio of volume divided by temperature is constant, or V1 over T1 equals V2 over T2. So whereas with Boyle's law, if you doubled the pressure, the volume would go in half. With Charles's law, if you double the temperature, the volume will also double. If you cut the temperature in half, the volume will also get cut in half. Now, what if you have a system that starts at 325 milliliters at 400 Kelvin and you cool it down to 300 Kelvin? Okay. Remember, with these gas laws, you always have to use absolute temperature, so it has to be in kelvins. If they give it to you in Celsius, you have to convert to Kelvin. Otherwise, you will die. All right. So V1 over T1 equals 2 over T2. It started at 325 mils and 400 Kelvin. We don't know what the final temperature is, but it ends up at 300 Kelvin. So our final volume is 325 times 300 divided by 400. So 325 times 3 divided by 4, 243.75 mils. Okay. So these initial gas law problems are fairly straightforward. They usually work out to something like this. A times B divided by C. Okay. All right, so now let us KMT sum Charles's law. What is the physical explanation? So the number of moles is constant, therefore the number of collisions is constant. Pressure is constant, so the force over the area has to be constant. But volume can change, therefore area can change, and temperature can change, therefore the force can change. So let's say we increase the temperature. What happens? The particles are moving faster, so each individual collision is now harder, so force increases. This means that the pressure inside the cylinder increases. This creates the imbalance, where the pressure inside is greater than the pressure outside, so the piston starts to move outward. Volume is increasing. As volume increases, you get more and more wall available, so the area increases, so that means that the pressure inside drops. Eventually, the pressure inside will be equal to the pressure outside, and the piston will stop moving. All right, now Avogadro's law, volume and moles. Pressure and temperature are constant. So that means that the pressure inside the thing won't change. The temperature doesn't change. So, okay, anyway. But volume and moles can move. So what happens if you add more stuff? Okay, obviously, I mean, this is one of the more obvious ones. You add more stuff, it's going to take up more space. Increasing the number of moles increases the volume. Decreasing the number of moles decreases the volume. That's obvious. What is less obvious is the fact that it is a very direct relationship. Double the volume, or double the moles means double the volume. Half the moles means half the volume. Or to put it another way, volume divided by moles is constant. Or V1 over N1 equals V2 over N2. So, how much space is occupied by 1.375 moles if half a mole occupies 12.5 liters? Well, V1 over N1 equals V2 over N2. We know V1, N1, and N2. We're looking for V2. So V2 is equal to V1, N2 over N1. So, 12.5 liters times 1.375 moles divided by 0.500 moles. 12.5 times 1.375 divided by 0.5 is a total of 34.375 liters. And yes, gases really do take up that much space. One of the things Avogadro discovered was that 1 mole of gas occupies 22.4 liters of space at atmospheric pressure and room temperature, under standard conditions, in other words. So, now let's go ahead and do the KMT thing. Pressure is constant, so force over area is constant, but force and area can both change. Now, the temperature is constant, therefore the individual collisions aren't getting stronger. But when you increase or when you change the number of moles, you're changing the number of collisions, so that will change the force. And of course, volume can change. So, when you increase the number of moles, you increase the number of collisions, increasing the force. This creates your initial imbalance. The pressure inside the cylinder is greater than the pressure outside, so the piston starts sliding out. This makes more wall available. The area increases, so pressure decreases. The collisions are getting more and more spread out. Therefore, eventually, the pressure inside will be equal to the pressure outside, and the piston will stop moving. Okay, so those are the 3 gas laws explained using kinetic molecular theory and a little sample of the math you can do for each of them. When we come back in a few minutes, we will move past the individual gas laws to the ideal gas law. See you then.